Okay, Professor.
Good afternoon. First of all, I would like to distribute some homeworks. I did not yet check the test, so I do not have the test results. And now, in the homeworks, if it does not say, I mean, if there is no grade, but it could say resubmit. Resubmit means to correct the material and resubmit the new material together with old material so that I will be able to compare the old version with the new version. Okay, if it says resubmit. Sometimes it could be just R. I did not check all the homeworks either, so not everyone is getting homeworks. Then I would like to make a note about the possibly very good textbook that you, in case you can get it by eBay or elsewhere. I think this is a good book, Vibrations. Vibrations book is called, and the authors are B. Balachandran and E.B. Magrab. Okay, Thomson Publishers. I think there is already a second edition. I like this book because the book uses functions for the beam. These functions K1 alpha x, K2 alpha x, K3 alpha x, K4 alpha x, but the book denotes it differently, different notation. So equation 980, I hope that I put, yes. Yes, equation 980 is using these notations. Okay, you may want to write it down. So this is Q of psi. So that is K1 of psi. So this is K1, K2, K3, K4, equation 980. You may want to write it down. But just letters are different. QRST. I saw that K1, K2, K3, K4 is better notation, just because it's easier to remember, and derivatives, how to calculate, it's easy to remember. But good thing, but that is not that important. I mean, the name. The main thing is that these authors are using these functions, which are very useful functions. So you may want to write K1 equals Q1, K2 equals R, K3 equals S, and K4 equals T. As I mentioned, these functions are introduced by some Russian mechanicist or mechanician, Krylov, but they found very wide application worldwide, everywhere. Okay? Still need to keep. a second note. Actually, I did not plan to give you back the homeworks, but let me write it down. Let us write down some notes, and I will use your homeworks back. Notes, let us write down notes on, what is our topic number? 28. Notes on Galerkin method. So I think I did ask you to consider clamped beam. Is it not? And in the clamped beam, I think people got the expression for the functions. May I ask your homeworks that I just gave you? Yes, just. Yes, for the clamped beam, students did obtain the following. Psi 1 equals x over L squared minus 2x over L cubed plus x over L in fourth power. So that was a homework assignment. And for simply supported case, okay, this first of all can be written as x over L equals xi, non-dimensional coordinate. Then psi 1 equals xi squared minus 2 xi cubed plus xi in fourth power. Okay, so that is this. And we can actually check this expression, whether this expression checking. So we should have w equals 0, so that means that psi 1 at 0 equals 0. So when xi equals 0, naturally this is 0 minus 0 plus 0, therefore it is 0. Now first derivative must be 0. So this gives us psi 1's first derivative equals 2 xi minus 6 xi squared plus 4 xi cubed. So when xi equals 0, psi 1 prime equals 0. So it's then w at L equals 0. But when x equals L, then xi equals 1, because xi equals x over L. And so we just calculate psi at 1 equals 1 minus 2 plus 1, and that naturally equals 0. You may want to write it down. Then psi prime at 1 must be 0. So let us calculate. That is this one. So that is 2 minus 6 plus 4. So this equals 0. So that is for clamped beam. Now for simply supported beam, I think we obtained psi 1 equals x over L minus 2 x over L cubed plus x over L in fourth power. So the difference is that this is in, so x over L equals xi. So we obtain psi 1 equals xi minus 2 xi cubed plus xi in fourth power. So then we satisfy psi 1 at 0 naturally equals 0. 0 minus 2 times 0 plus 0. Then psi 1 at 1 is 1 minus 2 plus 1, that also equals 0. Then second derivatives must equal 0. Okay? Psi 1 second derivative at 0, boundary conditions. And psi 1 second derivative at 1 must be 0. So we calculate psi 1 first derivative equals 1 minus 6 xi squared plus 4 xi cubed. Psi 1 second derivative equals 0 here, minus 12 xi plus 12 xi squared. So therefore psi 1 second derivative at 0 equals minus 12 times 0 plus 12 times 0. Squared equals 0. Psi 1 second derivative at 1, it is here I substitute, minus 12 plus 12 is also 0. Okay, so this function satisfies, and this is a function for simply supported column, simply supported beam. Then 3, I asked you to do the vibration analysis. Vibration analysis via Galerkin method for simply supported beam. Okay, so the results were like this. So omega squared were approximated as, if you remember, EI psi 1 fourth derivative psi 1 divided by rho A psi 1 psi 1. And these calculations yield, look, omega squared, so that is an approximation. So let us call it G, omega G squared. Omega Galerkin equals 3024 divided by 31 EI rho A L in fourth power. Or this is 97,548 EI rho A L in fourth power. Okay, that is by Galerkin method. Exact solution is omega 1 squared equals, as we know, pi over L in fourth power, EI over rho A. Or that is 97,4091 EI rho A in fourth power. So if I will put this omega square here, so what we get actually is this formula. Exact is pi in fourth, so that is not natural frequency. Natural frequency times rho A L in fourth power divided by EI. So that is this number. This is pi in 4, that is exact. (97,409). So approximate is 97,548. So approximate is somewhere here. So it's 97,548 approximate. So this is actually a general result. For Galerkin method. And that means omega 1 square Galerkin, or just omega Galerkin, is greater than omega 1 square. Why? Why is this? Differential equation and the boundary conditions had to decide about the mode shape. Okay. Differential equation. We had to satisfy differential equations, we had to satisfy boundary conditions, and that is how we should obtain mode shape. Instead, we imposed, as it were, on the beam how to behave. Thus, we increased its effective stiffness. And hence, omega 1 square, hence we obtained a higher estimate for omega 1 square. That is what has happened. Now I would like to assign you some more homeworks. Five. What is a set number? 15. Paying attention, please. I would like to ask you, there are some students who are using their own numbering. So now they are on set 19 or 27 or something like that. When I'm assigning 2 homeworks or 3 homeworks within one set, that is the whole set. You don't assign special number to every homework. Okay. Find the Galerkin estimate for the clamped beam and compare with exact solution. So that is homework. What does it mean? How many percentages approximation is greater than exact solution? So that is 15. We already have this psi1. Psi1, I think, is psi squared minus 2 psi cubed plus psi in 4th power. You had this as a homework already for psi1. That is 15a. 15b. Find psi1 for clamped free beam. So how do we do that? I think psi1 equals, say, a sub 0 plus a sub 1 psi plus a2 psi. Or maybe, sorry, we just write x, then x squared plus a3x cubed plus a4x in 4th power, and then satisfy the boundary conditions. Psi1 clamped free at 0 equals 0, d psi 1 dx at 0 equals 0. Then d2 psi 1 dx square at x equals L is 0, and d3 psi 1 dx cube at x equals L is 0. And then introduce psi equals x over L, and psi 1 is a function of psi. Okay, so that will be part B. Here, hi, psi, oh, psi 1, of course. Find psi 1, not psi 1, because psi is independent variable. Then C is find Galerkin estimate for omega 1 square and compare with the exact solution. So that is about Galerkin's method. Now, five, 6. And 29. How to obtain higher order Galerkin functions. Now, we just talked about one term. We talked about one term approximation. But there are many term approximations also. So in general, say we have this following equation, yes? EI d 4w dx in fourth power minus rho a omega square w equals 0. So in general, W is represented as some A k psi k of x, k from 1 to some n. Now n is number of terms taken into account. So it can be 10 or 20 or 2 or 1, etc. Then we substitute this here. We get, look please, EI, then we have summation, k from 1 to n, ak psi k fourth derivative, minus rho a summation, k from 1 to n, a, and here omega square. Ak psi k. Now this is not necessarily 0. Why it's not necessarily 0? Because we may not be so clever to just find some functions and you substitute and suddenly everything is 0. These are approximations. So therefore, this is an error. So then this error should be demands. So error must be perpendicular to psi 1 equals 0. So that is, error is perpendicular to psi 1. Then error perpendicular to psi 2, etc. Error perpendicular to psi n. Okay, so there are n conditions. So I will write down these conditions. Look, please. Looking here. Okay. So I will have A1. Yes. So A1. Then we will have EI psi k equals 1. Psi 1 force derivative, and this what I multiplied is psi 1. Yes. Then will be A2. EI psi 2 force derivative, psi 1, yeah, because I multiplied now by psi 1, plus a sub n ei psi n force derivative psi 1. Yes? But I did not take into account this term, so allow me to get rid of this, and I will rewrite this with this term also taken into account. Look, please. EI. Okay, so will be A1. I will take like this. And look, psi 1 force derivative psi 1, and I will take also this first term immediately. Minus rho A omega square, and then psi 1, psi 1. So that is A1. Plus A2. This EI psi 2 force derivative psi 1 minus rho A omega square psi 2 psi 1, etc. And then we will have A sub n. EI psi n force derivative psi 1 minus rho A omega square psi n psi 1. This equals 0. I will write second equation. A1 EI psi 1 force derivative. Second equation is I just multiply by psi 2 minus rho A omega square psi 1 psi 2 plus A2 EI psi 2 force derivative psi 2 minus rho A omega square psi 2 psi 2 plus etc. A sub n EI psi n force derivative psi 2 minus rho A omega square psi n psi 2 equals 0, etc. These are the equations. I just wrote only 2, but I can write, if you want, nth equation. So will be nth equation will be A1 EI psi 1 force derivative psi n minus rho A omega square psi 1 psi n plus A2 EI psi 2 force derivative psi n minus rho A omega square psi 2 psi n plus A sub n EI psi n force derivative psi n minus rho A omega square psi n equals 0. Have you ever seen so many terms together? Okay, let me reduce it. Okay, so we got n equations with n unknown. So, for example, in case of just two terms, then we demand, look please, did you write this? So imagine we have two terms only. If only two terms. So we get, look, A1, let us call it A11 plus A, okay, maybe B11. A2 B12 equals 0. Then A1 B21 plus A2 B22 equals 0. Okay, I can rewrite it like this. Only two terms. We want A1 and A2. This is a homogeneous set of equations. Now what does it mean? A1 equals 0, A2 equals 0, satisfy. Of course, if I substitute A1 equals 0, A2 equals 0, then of course it is satisfied. But we are not interested. In a trivial solution. Because W then equals A1 psi1 plus A2 psi2 and also equals 0. But I don't want mode shape that is 0. I want it to vibrate. So that this should be discarded. So therefore, we are saying that we are interested in non-trivial solution. Now, how do we solve this set of equations? We write down A1 equals, say, determinant. Okay, here denominator is determinant. B11, B12, B21, B22. Here, A1 I should write 0, 0, B12, B22. A2 equals the same determinant, B11, B12, B21, B22. Here, B11, B21, 0, 0. But this means that, look, 0 times B22, 0 times B1. So A1 equals 0 divided by B11, B12, B21, B22. A2 equals 0 divided by B11, B12, B21, B22. Okay, now that means that 8, 9, if determinant B11, B12, B21, B22 is not 0, then A1 equals 0 divided by non-zero will be 0. And A2 will be 0 divided by non-zero will be 0. Then we again get trivial solution. So in order system to have a non-trivial solution, it is necessary and sufficient that determinant must be 0. So we have like 0 divided by 0 that allows solution to be non-trivial. Maybe some other number. So we have B11, B12, B21, B22. This must be 0. That is a frequency equation. So in our particular case, will be like this. What is B11? B11 is EI psi 1 fourth derivative psi 1 minus rho A omega square psi 1 psi 1. B12 equals EI psi 2 fourth derivative psi 1 minus rho A omega square psi 2 psi 1. B21 equals EI psi 1 fourth derivative psi 2 minus rho A omega square psi 1 psi 2. And B22 equals EI psi 2 fourth derivative psi 2 minus rho A omega square psi 2 psi 2. So then it is B11 times B22 minus B12 B21 must be 0. Okay, or I will, okay, B11 times B22. So that will be, look, rho A squared omega in fourth power psi 1 psi 1 psi 2 psi 2. Okay, this times this. Then will be minus rho A omega squared. This, okay, I'm not going to calculate this, but you are seeing that that is a biquadratic equation. Biquadratic equation. And therefore we get two frequencies. Omega 1 square and omega 2 square. You see, if I take two terms, I can get estimates of two frequencies of the beam. When I took only one term, I could get only estimate of the first frequency. If I took two terms, I can estimate now two frequencies. So if I take 30 terms, I can estimate 30 frequencies. Naturally, calculation would be more difficult. Naturally, all calculations then should be conducted on the computer, not by hand. Okay? So that is, but it's a very powerful method. You may want to write down that there are finite element methods based on this method. There are finite element methods that are based on this method. And now maybe here just one small correction on 20. How to obtain higher order Galerkin functions, it should be corrected. How to obtain higher order frequencies. In the Galerkin method. Okay, please correct topic 29. Now we can deal with topic 30. How to obtain psi k. And so we know how to obtain psi 1, of course, yes? As you already did for simply supported case and clamped case, as well as I'm assigned you how to find for other boundary conditions. Now, let us investigate in more detail psi 1 that we obtained. Okay? So for simply supported beam, we had psi 1 equals psi minus 2 psi cubed plus psi in force power. So let us concentrate on this for a moment. So, first of all, let us forget for a minute the vibrations. Forget vibrations, that we are in vibrations class, we are dealing with vibrations. Let us remember statics. Static displacements. So equation is like this: EI d4y dx in force power equals qy of x. So now what is this qy of x? So that is this beam, and that is this load, distributed load, qy of x. Now we can actually non-dimensionalize. Non-dimensional coordinate, psi. Psi equals x over L, or x equals psi times L. Okay? Then we have, look please, EI d4y dx in force power, so that is d psi, and here will be L in force power, equals qy of x equals psi L. And so what I get actually is EI d4y d psi, okay, that is this, d psi in force power equals qy L in force power, something like that. So force, or y force derivative is some constant. Okay, because I divide by EI if this is uniform. So let us imagine that is constant, etc. Now, let us see what happens with simply supported case. Question: psi 1 in vibration mode of simply supported beam, to which loading qy does it correspond? I'm doing unbelievable. I found vibration mode. Fine. Thank you, psi 1. Then I said, forget vibrations. I will just want to calculate what static load produces such a vibration mode. So what I will do, I will just substitute it here and differentiate 4 times, and I will get the Q. So what we will get is as follows. Look, please. I want to calculate. So again, how much is psi 1 equals psi minus 2 psi cubed plus psi in force power. So let me differentiate. Once is 1 minus 6 psi squared plus 4 psi cubed. Psi 1 second derivative minus 12 psi plus 12 psi squared. third derivative. Minus 12 plus 24 xi. Fourth derivative. 24. So I got the fourth derivative equals to 24, or some number. That means that if qy equals 24 ei, and this is a beam, then, or qy is a constant. If qy is a constant, then I can actually like solve the following problem. So this is a constant. If you want 1. And solve this problem. Okay, solve this static behavior problem. Then why this function will be acceptable? Because look, that will be like psi, okay, ei psi fourth derivative equals 1. So this will be the fourth order polynomial because I have to integrate 4 times. It will satisfy all boundary conditions because I have to satisfy boundary conditions when I'm solving static problem. I cannot not satisfy. For example, it's also studied with me machine design or strength of materials. We have to satisfy all boundary conditions. So that means that in order to get psi 1, I can actually solve a static problem in order and put the load which is constant. I can also do different. I can just write the polynomial expression and then satisfy the boundary conditions from this polynomial expression. So that is what you did in the homework. But now I reinterpret it. So from here we are getting the following actually idea of getting psi's. So in order to obtain psi 1, I take this load. This is 1, for example, if you want 1. And I can also take ei equals 1. I don't want ei, etc., because I just want the function. It could be 1, or it could be 24. It could be 1 over 24 if I don't want